properties of discrete time LTI systems. In lecture 4, we dealt with properties of continuous time functions, and we touched a little bit on the discrete time systems. So we went up to here. So we are going to start with the properties of the convolution sum. And you say that the following properties of convolution sum are analogous to the convolution integral properties that we have seen in section 2.3. And the first property that we see is that the convolution sum is commutative. That if you do convolution of xn to h of n, it is the same as h of n convolved with of x of n. There is no difference. The other thing that as we saw in an analog, or rather in the continuous time case or LTI system, if you do an association where you do convolution between x and h1, and then you convolve with h2, the result will be the same as though you convolved the first two impulse responses, and then you take your signal and you convolve it with the two convolved system or impulse responses. This, if you are to draw this, it would be probably take this shape. You have x h1 of n. This is an LTI. This is system 1. Then you take it through as another LTI system, h2 of n, and then your input is coming here as x of n. The output will be the same. The output will be the same as y of n. If you did it differently, such that you still had your x of n as the input, and then you took it through h2 of n, but then after you took it through h2 of n, you take it through h1 of n, then the output will still be the same. So we are saying that the convolution sum follows the associative property. And the other idea that we do with we say in regard to the convolution sum is that it is distributive, such that if the input x of n is entered as at that point, which is h1 of n, and entered in parallel to h2 of n, then you sum the result. Then you sum the result. This is equivalent if you did it slightly different. Like if you took the h of n individually, or sorry, x of n individually, and then it goes to h1 of n, the result will still be the same. Like it will just appear like you're adding them after you have worked out the convolution after each entry. So x of n is entering at this point, and h2 of n, and you sum these two, the result is actually the same. So the convolution operation is as described. There's some steps that you do. We will see this in more details when you're dealing with examples. So I will avoid doing the operation here because the details are best understood when we do an example. And we can see, for example, 228 and 230 will show us that. So what we are also going to do at this stage is to see sorry. Just like we did with the continuous time LTI systems, the step response can be used to characterize a discrete time LTI system. And we normally know that the step response is the response of an LTI system when a unit step signal is applied at the input. So having said that, and we know how we can get the impulse response h of n for such a system, we can say that s of n, we consider, instead of the way we did, instead of saying that the input signal is x of n, or rather is an arbitrary signal, we say that the unit, or the input x of n is equals to u of n, which is the unit step input signal. So that being the case, if you just replace x of n in the convolution sum with u of n, this tells you something that we also covered, we also realized with continuous time systems. We say, if you remember, we said that the convolution integral changes from minus infinity to t for h of tau x of t minus tau. Oh no, it was not x. It was let me confirm this. It was initially the convolution integral was moving from infinity to, we were dealing with the impulse or unit impulse signal that was described by t minus tau d tau, and we said that for this to be unity, we require the term in the bracket to be equals to 0, and therefore we actually did some illustration and that said that tau requires to be less than t for requires to be less than t for this term to be equals to 1. In that case, we actually replaced our infinity with t as our upper limit. So that the same thing we are going to do, and now our t is going to vary from k is the one that is changing or replacing tau, and n is the one that is replacing t, and therefore our convolution integral will change from having in infinity to having n, and we said that when this has become 1, you actually remove it in entirety and you are left with h of tau. So in our case, our integration, our convolution integral varies from k being equals to minus infinity to being at n, and then our impulse response is now varying with k. So that serves us to illustrate how we are obtaining equation 240. And therefore, we are saying that we can obtain h of n. You can obtain h of n just like we did. If you remember what we did with the step response, we said that you can obtain the step response by integrating, this is integration, by integrating the impulse response, and we could obtain the impulse response from the step response by differentiating. So in a similar manner, we are saying that we can obtain the impulse response by getting the difference between the step response that is evaluated at n, where, or of course, and the step response that is shifted or delayed with a 1. So that will allow us to give to obtain h of n from the step response. So just like we looked at the properties of discrete time of the continuous time LTI systems, we are going to look at the properties of discrete time LTI systems, and we are going to start by finding out if the system has memory or it has no memory. And we are saying that since the output yn of a memoryless system depends only on the present input x of n, then if the system is linear and time invariant, this relationship can be of the form y of n is equals to kx of n, where k is a constant or gain that says that y will be, or y of n will be 0 if the input has not been applied or the input is 0. That is a very important statement that even allows us to determine if this system has memory. If y of n is not equals to 0 at x of 0, then this system is said to be has memory. This system has memory. In another way which you can do that is by introducing the concept of the impulse response. Here we are saying that the impulse response of that system, h of n, is simply given by k as long when the input is the unit impulse signal delta of n. It is something that we said, which I'm going to repeat again, that delta of n will be equals to 1 if n is equals to 0. And it will be delta of n, okay, I think we normally describe it simply using this kind of a bracket, will be equals to 0 if n is not equals to 0. So if we evaluate h of n, h and n naught, and we find that it is not equals to 0, and yet n is not equals to 0, then this condition is not satisfied, and that is when we say that it has memory. The next point that we want to discuss is causality, and causality simply means that the impulse response of the system will be equals to 0 when n is less than 0. That means if before the signal has been applied, we say that n is less than 0. So this is equivalent to before signal is applied. So if our h of n has some value that is not equals to 0, before or during this period, before the signal is applied, then we say that this system is non-causal. Otherwise, if h of n is equals to 0, when n is less than 0, then we say that it satisfies the condition of causality, and we say that the system is causal. The other property that we are going to discuss in regard to the discrete time LTI system is that of stability. And the concept of stability says that if you have a bounded input x of n, which is less than infinity, and it gives you a bounded output y of n, that which we describe as being less than infinity, we say that this system described by t or h is said to be stable. Otherwise, if you give, okay, for instance, you have h of n, and you have given it an input x of n, which is bounded, then if this is your system T, if or LTI, if this system gives you a y of n that is approaching infinity, that system is said to be or unstable. The proper word is unstable. Now, to discuss the eigenfunctions of a discrete time LTI system, we follow the same idea like we did with continuous time LTI system, except that we are using a different complex exponential that was obtained in problem 145, which we have not done, but we will find some time to do. If we just take it as stated, that a discrete time LTI system represented by T has an eigenfunction Z, which is a complex exponential Zn with Z as a complex variable, that which is now expressed as this one. I want to just write it. We are saying that an eigenfunction of the discrete time LTI system represented by T, so this is the operator that is acting on our eigenfunction Z of n, then it will have eigenvalue lambda, which is acting on the eigenfunction Zn again. And we want to find what the question is asking, what is our eigenvalue that will characterize our system. And we can simply do this by setting our x of n, our arbitrary input, to be equals to Zn, as has been stated at that point. And when we do that, we end up with having y to be equals to y we said is acting on, y of n is acting on T, which is x of n, but we have defined x of n to be equals to Z of n. Therefore, I'm writing it as T Z of n as such. And therefore, by definition, we know that T is defined as the impulse response, which is described by the convolution sum as having k from minus infinity to infinity of h of k Z, our x of n is a function of n minus k, but if we replace x of n with z of n, you will have n minus k. That describes our convolution integral, which we can simplify further by simply stating that n is not a function of it's supposed to be k. N is not a function of our summation of our integral, and therefore what we will end up with is removing Zn from the summation, and we have k from minus infinity to infinity, and we simply express this one as h of k z of minus k. And if we look at now this case very keenly, what you'll observe is that this expression is in the form of our area function, which is y of k, y of n, that is, we are saying if you compare this equation with this equation, you'll find that this term is the one that we have removed and we have placed outside the bracket, and therefore our t is our convolution integral, and therefore we can say that this 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 summation is equivalent to our lambda, which was described by t, and that becomes our eigenvalue of our impulse response of our LTI system. And therefore, from that point, we are simply saying that we can express this to be our lambda and z to be our initial function. And therefore, as you can see, z lambda is equal to h of z, and that is our eigenvalue, which is given by this term that we have just evaluated. And that means the eigenvalue of a discrete time LTI system associated with the eigenfunction z of n is given by h of z, which is a complex constant whose value is determined by the value of z that we have defined in equation 252. We also note that from equation 251 that if you set your n to be equals to 0, if you set your n to be equals to 0, what you will find is that this term gives you a 1, and therefore your y of 0 will be equals to h of z, which is defined by our eigenvalue. That's a very significant representation, because it kind of gives you the initial value or the initial condition for our differential equation. And we're saying that this result is very significant because it defines for us the Z transform that you'll probably deal with in another class or another unit, probably DSP. But we're going to be dealing, even the discrete Fourier transform, DFT is going to be dealt with in this class. This is a 5th year unit, so for now we are not going to dwell much with them. We are only going to be dealing more with the Fourier transforms in continuous time. So that marks the end of our first section of lecture 5. We will pause and resume at section 2.9 that describes the systems using difference equations.